We'll now look at another application where the output location changes the transfer function, changes the way the poles and zeros are arranged. And this problem is a high-speed spindle on magnetic bearings. This was a research project I worked on some time ago. The spindle is used to cut metal, and the goal was to support it on magnetic bearings so that it could spin at very high speed and so that its vibration could be well controlled. The magnetic bearings would hold the spindle in place. There would be no ball bearings or fluid bearings. The shaft would be completely controlled by a magnetic field, levitated in place as it spun at 30,000 RPM. To accomplish this, there were 3 radial bearings to control the radial motion of the spindle at different locations, and 1 axial bearing to control its motion along its axis. These bearings are shown at the bottom of the photograph, along with the stator of the motor. Here is the spindle itself. This is the part which we've magnetically suspended, and this is the part of interest to us from the point of view of poles and zeros. There are various points at which forces could be applied to the spindle, principally the locations of the magnetic bearings. There is one at the front of the spindle, which is on the left side, one in the center, and one at the far end, on the right side. These locations are locations where magnetic forces would be applied. We're interested in the transfer functions between these locations and various locations along the shaft. And depending upon what input and output locations we have for the input forces and the output displacements, we'll get different transfer functions. And these transfer functions will have different zeros. The poles will always be the same, although sometimes a mode may be unobservable, like we saw in the tilting beam problem. So here is the first transfer function we'll examine. We have an input force acting at the center bearing, and we're going to look at an output acceleration at the nose bearing. Now this output acceleration was measured with an accelerometer attached to the spindle. The spindle is hit at the location of the input force. This is the kind of vibration testing which is commonly done in industry, and it's referred to as impact testing. From this, we measure the impulse response, and then the impulse response is Laplace transformed to find the transfer function. That is then plotted, both magnitude and phase. We'll be looking at just the magnitude plots. Here is the experimentally obtained frequency response, the solid black line, along with the dashed black line, which is the response predicted by a model we made. You can see the poles and zeros of this frequency response. The poles indicated by the red arrows, the zeros indicated by the blue ones. And what you'll notice is the interlacing property we discussed before. We have zeros between the poles. Each resonance here corresponds to a pair of poles near the imaginary axis. These pairs of poles are modes, vibratory modes, of the system. They correspond to a natural vibration of the system, a vibration which involves bending of the spindle shaft. There are 2 things I'd like you to particularly notice about this frequency response. The first is that the lowest frequency, 0, is above the frequency of the first resonance. The second is that there is a 0 and a pole shown here, which are very close to each other in frequency. So there's a 0 close to the frequency of the second resonant mode. Now we'll look at another frequency response. And here, the output location is the same as before, but the input location has moved. I now have my input force at the front bearing, not the center bearing. And so, the transfer function will be different. It will be different because the zeros will be different. The poles are unchanged by where the input and output are located on my structure. Let's see how the frequency response of the system has changed because of the different zeros in the transfer function. There are two important differences between this frequency response and the one we saw before. The first is you'll notice there's now a pair of zeros with frequency lower than the first resonance. And second, we have a missing resonance. There's a pole zero cancellation. The second bending mode resonance is now disappeared from the frequency response. This is because a pair of zeros now lie very close to the pair of poles of this resonance. Here we summarize these results, showing the input locations and the output location and the corresponding frequency response plots. The important thing to realize here is that the frequency response is strongly affected by where the input and output locations are in a mechanical system. The reason why it is affected is because these choices have an effect upon the zeros. The poles will remain unchanged. Depending upon where the input and output location are, one can make a pair of zeros lie on top of a pair of poles for a flexible structure, and thereby hide one of the resonances, that is, to make one of these modes unobservable or uncontrollable.